Okay, given a set of vectors in Rn and a set of scalars, real numbers, the vector y that's defined by c1 times v1, so that constant multiple of v1, plus c2 v2, plus c3 v3, all the way out to cp vp, is called a linear combination of the vectors. The weights are those constants, those scalars, c1 to cp. Now, the vectors individually are in Rn. I've got p different vectors that I'm taking the linear combination of. So don't confuse the fact that I have p vectors. They're all in Rn, meaning each one of those has n entries. Now, the weights in a linear combination can be any real numbers, including the number 0. So an example, if I had two vectors, let's just look in R2. So I've got u, which would be 1, 3. V is equal to 2, 5. Pick any scalars you want. Well, let's say I pick 2 for C1 and 0 for C2. This is a linear combination of u and v. I used my weights of 2 and 0, and so that just gives me the vector 2, 6. So 2, 6 can be written as a linear combination of u and v. Okay, so the weights are just the constants that are being multiplied by the vectors. Okay, so now the figure below identifies linear combinations of v1, which is negative 1, 1. So let's look at negative 1, 1, which is this vector right here. So that's v1. Okay, multiples of v1 then, we noticed previously that they're either in the same or the opposite direction. So 2v1 is going to be going in the same direction as v1, but twice as long. 3v1 would be going in the same direction, but 3 times as long. Okay, so 2v2 ends here, and 3v1 ends here. Okay, now let's look at v2. Should be a 2. v2 is the vector 2, 1. So if you plot it, this is what they're saying v2 is. So that's 2 over and 1 up. Multiples of v2, well, 2v2 is in the same direction but twice as long. 3v2 would be 3 times as long, so it starts at the origin and is going all the way out to here. Negative 1 times v2 would be going in the opposite direction but the same length as v2. Negative 2v2 would be coming here from the origin out to here. I didn't do the negatives on v1. Negative v1 is the same length as v1 but the opposite direction. Negative 2v1 again starts at the origin and it goes out twice as long as v1 in the opposite direction. Okay, so now those lines are multiples of v1 and v2. Okay, if I want to find linear combinations of v1 and v2, then I'm taking any constant multiples of those two vectors. So all the other points in the plane can be written as a linear combination of the vectors v1 and v2. So let's see how that works. They've got a vector u here. We can look at that as the vector u, or we can look at it as the point in the plane. So the vector u can be written as a linear combination of v1 and v2. So let's see if we can figure out what weight of v1 and what weight of v2 would have to be summed to get the vector u. So the vector u, again, is the vector that starts at the origin and ends at this point u with the arrow pointing to that point. Okay, so now to determine the multiples, the linear combination of v1 and v2, look at the grid that we formed. Okay, so it's like we've defined a new coordinate system using v1 and v2 as one unit in each of those two new axes. So look at the point U and look at the grid determined by v1. We had 0 here, v1 here, v2 here, v3 here. By looking at the grid, we would have to come out 3v1 to get even with this point u. So I'm going to propose that 3v1 is the proper weight of v1 to create u. So now what about the v2? Well, again, moving parallel to v2, we have all these other lines, this grid. These are all parallel to v2. Okay, so v2 then, if we start here at the 3v1, the tip of 3v1, if we added 1v2 to that, we would be over here at this point. But we want to add negative v1 because we want to go in the opposite direction. So here's negative v1 added to 3v1, negative 2, notice the 2 units here. We've got 2 of these units. This is a unit in that direction parallel to it. So negative 2 v2 added to 3v1 gives us the vector u. So again, think of it as a coordinate system. v1 takes you out however far this direction you want to go. You just figure out what the multiple is, how many of the v1s you have to go to line up with that u, and then do the same for the v2. This is the direction, and you're just going parallel to it, but you've got to go in the opposite direction of v2, and you've got to go 2 of those units, where v2 is considered 1 unit. Okay, now let's look at w. Where is w here? Okay, here's w. Let me get rid of all these other lines. W is here. And I want to figure out how many v1s and how many v2s would be needed to create w. So it's going to be a linear combination. Every point in that plane, in those 2 dimensions, can be written as a linear combination of v1 and v2. Now, that would not be the case if they were parallel to each other, but they're not. As long as they're not parallel, every point in that 2-dimensional space will be a linear combination of v1 and v2. So let's see. To get to w, I need to go out. So you can also think of it as if you were traveling along streets. So from the origin, I need to go out 1v1, 2v1, and maybe another half of v1 to line up. And then how many v2s? Well, to get to the w, I'm going to have to go to the left side, which is in the opposite direction of v2. Remember, v2 is over here heading to the right. So I need to go about half to the left. So that would be, let's see, I've got 2.5, so 2.5 v1s in the same direction, and then minus or plus a negative 1/2 v2, and that would give us our vector w. So you could write it as 5/2 v1 minus 1/2, or you can say plus a negative. Subtraction is just adding the negative of the vector. Okay, so let me get another one here that we can estimate. What if we had the point right here? I want to be able to write that as a linear combination of v1 and v2. Well, let's see how far out along the same direction or opposite direction of v1 would I need to go to get to that point. Well, let's see. Looking at my grid, I'd need to go this way. So you want to think of 2 blocks in that direction. You can only stay along those grids. So that would be negative 2 v1s. And then what would I need to add to get to how many v2s? Well, I'm going to have to go this direction, which again is in the opposite direction of v2, and it's 1 unit. So that would be plus 1 v negative 1 v2. And that would be I'll call this the point z. And let's pick one more here. Let's say we were looking at this point right here. Okay, think of the grid as being the way we have to travel, like the streets that we can travel down. To get to that point, I'm going to have to go, let's look first at the v1 level direction. I would have to go this direction. Some of these other marks. I would have to go in this direction 1 unit, so that's negative 1 times v1, and then I would have to go parallel to V2 twice as 2 units of V2. And we'll just call this one Y. Okay, so linear combinations generate the entire XY plane, or the entire two-dimensional space. So think of a linear combination as, just a point in the span. Well, we haven't talked about span yet. A point in the space that V1 and V2 are determined in, and they're determining the coordinate system. What units are and what the directions are. Okay, I want to see, can B be generated as a linear combination of A1 and A2? Well, for B to be a linear combination of A1 and A2, that means that there has to be some C times A1, so C1 times A1 plus C2 times A2 that's equal to the B. That's what it means to be a linear combination of A1 and A2, because this is a linear combination of the two vectors A1 and A2. Okay, so what does that look like then? Well, algebraically, this is C1 times the vector A1, which is 1, negative 2, negative 5, plus C2 times the vector A2, which is 2, 5, 6, and we want that to be the vector 7, 4, negative 3. All I'm doing is I'm looking at this vector equation and filling in the vectors. Okay, now we know what scalar multiplication is. This is just equal to C1, negative 2C1, negative 5C1, 2C2, 5C2, and 6C2. Well, we also know how to sum vectors together. This is equivalent, the left side is equivalent to C1 plus 2C2, minus 2C1 plus 5C2, and minus 5C1 plus 6C2. Now, for two vectors to be equal, that means the components have to be equal. Well, this is equivalent to C1 plus 2C2 having to be 7. The second components, negative 2C1 plus 5C2, would have to be 4. And minus 5C1 plus 6C2 is equal to negative 3. So now all we've got is a system of equations, and we want to find the weights, C1 and C2, that make that true. So if B is a linear combination of A1 and A2, there have to be C1 and C2s that make this system true. So remember how we did this back in the last chapter, or in the last section. We created an augmented matrix. I took the coefficients of the C1, the unknown C1 and C2. So we had 1, 2, negative 2, 5, and negative 5, 6. And then I appended the constant terms from the right side of the equation. And so this was our augmented matrix. And then we just row reduced it. So you could use your calculator. I'm going to go ahead and do this one by hand. Okay, I'm going to keep first row the way it is. I'm going to take twice, 2 times row 1, and add it to row 2. And that'll be my new row 2. So 2 times 1 is 2, added to negative 2 is 0. 2 times 2 is 4, added to 5 is 9. 2 times 7 is 14, added to 4 is 18. And then I'm going to take 5 times row 1, added to row 3. So 5 times 1 added to negative 5 is 0. 5 times 2 is 10, added to 6 is 16. 5 times 7 is 35, added to negative 3 is 32. Row 2, I'm going to change to 0, 1, 2 by multiplying through by 1/9. And now I'm going to take, notice I could change row 3 to 0, 1, 2 also if I wanted to make the numbers a little smaller, but I'm fixing to change those anyway. So now let me take negative 16 times row 2 and add it to row 3. So it's going to keep that as a 0. I'm going to have negative 16 and 16. I'm going to have negative 32 and 32. Okay, now the last thing I'll do is zero out the 2 up here by multiplying -2 times row 2, this new row 2, and adding it to my row 1 to get the new row 1. So 0 added to the 1, -2 added to 2, -4 added to 7. Okay, and so this is our matrix. If we were rewriting this, remember C1 and C2 are our unknowns, so this would be equivalent to the vector, the last row, it doesn't matter. We've got 1, 0, 0, 1 times C1, C2 equal 3, 2. I'm ignoring the last row. We only have 2 unknowns, so we really only need 2 equations, which, if there's a solution, then that was a solution to that original problem. So we see here that C1 is equal to 3 and C2 is equal to 2. So those would be the weights of vector A1. So that means that 3 times this vector plus 2 times this vector should equal to that vector. So 3 plus 4 is 7, -6 plus 10 is 4, -15 plus 12 is -3, and that does it. So, generalizing that, notice that the original vectors A1, A2, and B ended up being the columns of that augmented matrix. So if you go back here, look at the columns over here. This is A1, and this was my A2, and here was my B. So if you're trying to solve this problem of determining weights of A1 and A2 that create the B, or what linear combination of A1 and A2 gives you B, just simply put the vectors A1 and A2 in columns of a matrix and the B in another column. So this will create the augmented matrix. So now we can write this, if we want to just abbreviate it, we can just write it as, instead of having to write out all the columns, we can write it as saying, okay, put A1 in column 1, A2 in column 2, and B in column 3. So just realize in this form that those are vectors in the columns. So that's not a 1 by 3 matrix. That's actually an n by 3, depending on what are in space A1, A2, and B are in. Okay, so if you're solving this vector equation, it has the same solution as if you put the vectors, see, x1, x2, and xn are the weights, and you're just putting the vectors in the columns, including what those constants are on the right side. So this vector equation has the same solution as the linear system does that has this augmented matrix. Okay, so in particular then, B can be generated as a linear combination of A1 up to AN if and only if there's a solution to the linear system that corresponds to this matrix. So we can solve to see if something's a linear combination by just solving a matrix, a linear system given by a matrix.